In this video, we're going to talk about subgroups of groups. As you would probably assume, a subgroup of a group is just a subset of the group that's also a group with respect to the same binary operation. However, because there are some technical points in that statement that need to be clarified, the original definition that we're going to give is going to look a little bit different, but it's going to turn out to be the same in the end as what I just said. Here is our official definition. Let's suppose that G is a group, which we'll assume is written multiplicatively. Well then, we say that a non-empty subset H of G is a subgroup of G if two conditions hold. The first condition is that for every pair of elements little g and little h in H, the product of G and H must lie in H. And the second condition is that for every G in H, the inverse of G must lie in H. Of course, the product and inverse here are taken using the binary operation and group structure on G. We'll refer to the first property by saying that H is closed under multiplication, and we'll refer to the second property by saying that H is closed under inverses. A convenient notation for denoting that H is a subgroup of G is to write H less than or equal to G. Now, the first thing that I want to convince you of is that these conditions guarantee that H is a group with respect to the binary operation on G, so that this definition matches our intuitive understanding of what a subgroup of a group is. Let's go through the details of this claim just to verify that it's true. So we're assuming that H is a subset of G, that H is non-empty, that H is closed under multiplication, and that H is closed under taking inverses. And we'd like to show that these conditions guarantee that H is a group with respect to the binary operation on G. Well, the first point, which is a little easy to overlook, is that condition number 1 guarantees that the restriction of the binary operation to H is actually a well-defined binary operation on H. If condition 1 failed to hold, then it would mean that we could find two elements of H with the property that when you multiply them together, you leave H. That would mean that the binary operation on G is not a well-defined binary operation when we restrict to H, and so then the statement that H is a group with respect to that binary operation wouldn't even make sense. Therefore, we need condition number 1 to guarantee in the first place that this is a well-defined binary operation on H. Now, once you know that the binary operation is well-defined, the associativity of the restriction of the binary operation to H follows directly from the associativity of the binary operation on G. That's because a product of any three elements in H is also a product of three elements in G, and we already know that it doesn't matter how you put the parentheses on when you're multiplying three elements in G. So associativity is immediate in this case. Now, the next thing that we need to show in order to establish that H is a group is the existence of an identity element. So here is where we need to use the fact that H is non-empty. If H were the empty set, then there's no way that it could be a group. So it's necessary to assume that it's non-empty here. And the fact that it's non-empty means that there's an element G in H. Well then, condition number 2 guarantees that the inverse of G in the group G is also an element of H. And then condition 1 guarantees that G times G inverse is also in H. But G times G inverse is the identity in the group G. And we know that the identity has the property that for any element H in H, when you multiply it by E sub G, either on the right or on the left, you just get H. Therefore, E sub G plays the role of an identity element in H. And so, perhaps not too surprisingly, the identity in H turns out to be the same as the identity in G. And as long as the conditions above are satisfied, it's guaranteed to always be an element of H. Now, the final thing that we need to check in order to verify that H is a group is existence of inverses. But this one comes almost for free by condition number 2, because condition number 2 guarantees that for any G in H, the inverse of G in G is also in H. But since the identity in H is the same as the identity in G, the inverse of G in G is going to be the same as the inverse of G in H. That establishes existence of inverses, and it completes our verification of the claim that the conditions above guarantee that H is a group with respect to the binary operation on G. Now let's look at some examples of subgroups. So for our first example, let's take the group G to be the group of integers, and let's take the set H to be the set of all even integers, which I'm denoting here by 2z. So 2z is the set of all things of the form 2k, where k runs through the integers. Now we claim that H is a subgroup of G, and so in order to check this, we need to know that first of all H is non-empty, which it is, and then we need to check that it's closed under multiplication and closed under taking inverses. The thing to be careful of here, though, is that the group operation on this group is addition, And so when we say closed under multiplication, here we really mean that H is closed under addition. And when we say closed under inverses, here we really mean closed under negatives. Hopefully this is not too confusing, but this switching back and forth between multiplicative and additive notation is something that you have to deal with again and again in group theory. So let's suppose that we have two elements G and H of H, and let's suppose that G is 2k and H is 2L for some integers k and L. To show that H is closed under addition, just notice that when we form G plus H, the 2 factors out and we obtain 2 times k plus L. But since k plus L is an integer, that shows that G plus H is an element of H. And that means that H is closed under addition. Similarly, if we take the negative of G, that's just going to be 2 times negative k, and since negative k is an integer, negative G is also an element of H, so H is also closed under taking negatives. Since H is non-empty and it satisfies both of the conditions in our definition, we see that H is an example of a subgroup of the group G. Now, it's worth pointing out in this example that the integer 2 here is not really special, and in fact, if we take H to be nz, where n is any integer, so in other words, H is the collection of all integer multiples of n, then by almost the same arguments with the 2's replaced by n's, we can see that H is going to be a subgroup of G, and it's the subgroup consisting of the collection of all integers that are divisible by n. Now, 2 special cases to point out here are when n is 0, in which case H is just the subgroup consisting of the single element 0, and when n is plus or minus 1, in which case H is all of z. For all other choices of n, the subgroup nz is going to be an infinite subgroup of G, which is not equal to all of G. For our second example, let's take G to be the cyclic group of order 6, and let's assume that this group is written multiplicatively and that a generator for the group is the element x, so that the elements of the group are all the powers of x starting from x to the 0 and going up to x to the 5th. What are some subgroups of this group? Well, one subgroup is the subgroup consisting just of the elements identity and x cubed. And you can see that pretty easily because if you multiply together any 2 elements of this set, like identity times identity or identity times x cubed or x cubed times x cubed, which is the same as the identity, then you stay in this set. So it is closed under multiplication. And it's also closed under taking inverses because the inverse of the identity is just the identity, and the inverse of x cubed in this case is just x cubed because of the condition that x to the 6th power is the identity. So this is one example of a subgroup of the cyclic group of order 6. Now, another example is the set consisting of the identity x squared and x to the 4th. And here again, you need to go and check that this set is closed under multiplication and closed under the taking of inverses. Closed under multiplication is pretty easy to do, and so is closed under taking inverses, since the inverse of x squared is x to the 4th and the inverse of x to the 4th is x squared. So this is another subgroup of the cyclic group of order 6. Next, let's take the group G equals the Klein 4 group, which we'll assume is given to us with the presentation having generators A and B and relations A squared equals B squared equals identity and AB equals BA. If you can't remember what this means or how this group is defined, you can see our video on groups of orders 4 through 8. But when you work it out, this turns out to be a group of order 4, whose elements are the identity A, B, and AB. And all of these elements have the property that when you square them, you get the identity. So what are some subgroups of this group? Well, for one subgroup, I can take the set consisting of the identity and the element A. Now that's clearly closed under multiplication, and the only thing that you really need to check is that when you multiply A with itself, you stay in the set, but A squared is the identity element. Also, this set is closed under taking inverses, and once again, the crucial point here is that the inverse of A is just A. So this is an example of a subgroup of V4. Now, for the same reasoning, if I take the set consisting of the identity and the element B, that's another subgroup of V4. And if I take the set consisting of the identity and the element AB, that gives me yet another subgroup of V4. Now for our next example, let's take the dihedral group of order 2n, where n is an integer greater than or equal to 3. And let's suppose, as we did in the video on groups of orders 4 through 8, that this group is given to us with the presentation consisting of the generators R and S subject to the relations that R to the n is S squared is the identity and Rs equals SR inverse. Remember also that this is the group which describes the collection of all rigid motions of a regular n-gon centered at the origin in the plane. And also that when you list out the elements of this group, you just get the collection of all rotations of the regular n-gon, which correspond to the elements identity r out to r to the n minus 1, and then the collection of all compositions of a reflection and a rotation, which are the elements of the form s sr out to sr to the n minus 1. So these are the 2n distinct elements of the dihedral group of order 2n. And now, what are some subgroups of this group? Well, if you just look at the first n elements here, it's pretty easy to see if you just put them all into a set, they're going to form a subgroup, and that subgroup corresponds in our geometrical understanding to the collection of all rotations preserving a regular n-gon centered at the origin. It's a cyclic group of order n generated by the single element r, and it's easy to see that it's closed under multiplication and closed under taking inverses, since r to the n is the identity. Now, another obvious subgroup of this group is the group that you get by just taking the identity element and the reflection s. And again, it's guaranteed that this is closed under multiplication and taking inverses because s squared is the identity. Now, there are more interesting subgroups of this group, and we'll talk about them later in the video. Now I want to talk about some important facts and terminology. Let's suppose that G is a group. One fact which you may have already noticed is that G is always a subgroup of itself, and the set consisting just of the identity element of G is also a subgroup of G. So every group is guaranteed to have a subgroup, and the subgroup consisting of just the identity element is called the trivial subgroup of a group. Second, a point of terminology. If H is a subgroup of G which is not equal to the whole group, then it's called a proper subgroup of the group. So just remember that for future discussions. The next important fact, which is often useful for simplifying proofs, is what's called the subgroup criterion. And what it says is that if you have a non-empty subset H of a group G, then to check that it's a subgroup of G, you only need to check that for every G in H, G times H inverse is an element of H. Now, this condition is obviously going to be satisfied if H is a subgroup of G, and so this gives you an equivalent characterization of what it means for H to be a subgroup of G. A non-empty subset is a subgroup of G if and only if for every G in H, G times H inverse is an element of H. The proof of this is pretty easy, and it's a good exercise to reinforce that we understand the definitions, so let's go through it really quick. So first of all, as I already remarked, if H is a subgroup of G, then because H is closed under multiplication and taking inverses, it's guaranteed that for every G in H, H inverse is in H, and then G times H inverse is in H. So the left-hand side easily implies the right-hand side, and what we really want to show is that if the right-hand side holds, then the left-hand side holds. Therefore, let's suppose that H is a non-empty subset of G for which the right-hand side of this biconditional statement is satisfied. Now, the fact that H is non-empty means that there exists an element G in H. And then, letting G play the role of both G and H in the statement on the right-hand side here, we find that G times G inverse is in H. But G times G inverse is the identity element in G. So that shows that the identity element is an element of H. Now, although that's not one of the two conditions in the definition of subgroup, this is an important linking step to showing that H is closed under multiplication and taking inverses. So second, we're going to show that H is closed under taking inverses. Suppose that little h is an element of H, and apply the condition on the right-hand side here with G equals the identity element, which we know is an element of H, and with H equals H. That gives us that the identity element times H inverse is an element of H. But since the identity times H inverse is equal to H inverse, that guarantees that H inverse is an element of H. So it shows that H is closed under taking inverses. Now finally, to see why H is closed under multiplication, let's suppose that G and H are two elements of H. Well, since we already know that H is closed under taking inverses, that means that H inverse is also an element of H. And what I'd like to do now is to apply the condition on the right-hand side here with G equals G and with H equals H inverse. That gives me that G times H inverse inverse is an element of H. But since H inverse inverse is just H, that guarantees that G times H is an element of H, which means that H is closed under multiplication and is therefore a subgroup of G. That establishes the statement of the subgroup criterion. And it means that when you want to check that a non-empty subset of a group is a subgroup, instead of checking two things, you only need to check that for every G in H, G times H inverse is an element of H. Now, if H is a finite non-empty set, then the situation is even a little better. And to check that H is a subgroup of G, we can use the subgroup criterion for finite sets. The subgroup criterion for finite sets says that if you have a non-empty finite subset H of G, it's going to be a subgroup of G if and only if it's closed under multiplication. Now, once again, it's clear that if H is a subgroup of G, it has to be closed under multiplication. But the point here is that when H is finite, you don't even need to check that it's closed under taking inverses. If it's closed under multiplication, then that will automatically guarantee that it's a subgroup of G. So let's take a look at the proof of this one. As mentioned, we're trying to show that if H is a non-empty finite subset of G which satisfies the condition on the right, then it's automatically a subgroup of G, and what we need to check is that such a set H is closed under taking inverses. So choose your favorite element G of H, and consider the set consisting of all positive powers of G, G to the 1, G squared, G cubed, and so on. Because we're assuming that H is closed under multiplication, all of the elements of the set must be elements of H. But because H is finite, there must be at least one element in this list which is repeated infinitely often. So that guarantees that we can find natural numbers I and j, with j bigger than or equal to I plus 2, with the property that g to the I is g to the j. Well then, if I multiply both sides of this equation by g to the minus I find that g to the j minus I is the identity element. But g to the j minus I is g to the 1 times g to the j minus I minus 1, and that tells me that the inverse of g is g to the j minus I minus 1. Now the reason why I wanted j to be at least I plus 2 was in order to guarantee that this exponent j minus I minus 1 is bigger than or equal to 1 at this step. And since that holds, I'm now guaranteed that g to the j minus I minus 1 is an element of this set, so it's an element of H. That shows that the inverse of any element of H is also an element of H, so it completes the proof of the subgroup criterion for finite sets. The next important fact that we want to establish is that when you take an intersection of a non-empty collection of subgroups of a group, what you get is also a subgroup of the group. This is an important fact, and it applies not only when the indexing set here is finite, but even when it's an infinite set of arbitrary cardinality. Now, the adjective non-empty here just means that the indexing set capital I is non-empty, so that there's at least one subgroup here that we're intersecting. Otherwise, we would have the empty set, which we know is not a subgroup of G. So let's go ahead and try to establish this fact. First of all, let's write H for the intersection of all of the HIs. The first thing that we'd like to check is that the set H is non-empty, and this is an important step because remember, an empty set can never be a group, since every group must contain an identity element. Well, that's also a hint about how to prove that the set H is non-empty, because since every group must contain an identity element, and since the identity element of any subgroup of a group G is the same as the identity element of the group, we know that the identity element of G must be an element of HI for every I in I. But then by the definition of intersection, the identity element is an element of the intersection of all of the sets, which allows us to conclude that the set H is a non-empty set. Next, we'd like to use the subgroup criterion to show that the set H is a group. So suppose that G and H are elements of H, and what we want to show is that GH inverse is also an element of H. Well, if G and H are elements of H, which is the intersection of all of the HIs, then G and H must be elements of HI for every I in I. Now, since each of the HIs is a group, by the subgroup criterion we have that GH inverse is in HI for every I in I. But if GH inverse is in all of the HIs, then it's in their intersection, so GH inverse is also in H. That's what we wanted to show, so now we can conclude from the subgroup criterion that H is a subgroup of G. Now, I also want to mention here that while this fact is true, that intersections of subgroups are subgroups, it's not true in general that unions of subgroups are subgroups. So you have to be a little bit careful. I'll leave that as something for you to think about. Next, I want to talk about a very important concept, which is the concept of a subgroup generated by a subset of a group. So let's suppose that we have a subset S of a group G. Then the subgroup generated by S, which we'll denote by triangular brackets S, is defined to be the intersection of all subgroups of G which contain the set S. Now, the first thing that I'd like to mention about this definition is that there's always at least one subgroup of G containing the set S, which is the group G itself. So the intersection in this definition is an intersection of a non-empty collection of subgroups of G, which we know by the fact that we just mentioned is going to produce another subgroup of G. So as the name indicates, the subgroup generated by a subset of G is always a subgroup of G. The second thing that I'd like to mention, which is another important way of thinking about the subgroup generated by a set, is that the subgroup generated by S is the smallest subgroup of G containing S, in the sense that if H is any subgroup of G which contains S, then since H is an element of the intersection in this definition, H must contain the subgroup generated by S. This is an important fact which we'll use later in the video. The next point, which is a matter of notation, is that when the set S is a finite set, say consisting of the elements G1 to Gn, then instead of writing triangular brackets S for the subgroup generated by S, we may also just write triangular brackets G1 to Gn without the curly braces on the inside. Now this is consistent with the notation that we introduced back when we talked about cyclic groups in our video about groups of orders 1 through 3. But now that we have the definition of subgroup, we're going to refer to the group generated by a single element G as the cyclic subgroup generated by G. Next, a small but important definition. If there's a finite subset S of G with the property that G is generated by S, then we say that the group G is a finitely generated group. Now, to avoid confusion early on here, I want to point out that for a group G to be finitely generated is not the same in general as for it to be finite. So on one hand, if you have a finite group, then it is going to be finitely generated, because every group is generated by the set consisting of all of its group elements. However, the converse of this statement is not true in general. In other words, there are examples of finitely generated groups which are themselves infinite groups. Or, to put it another way, just because a group is infinite, you can't conclude in general that it's not finitely generated. It's easy to come up with examples of infinite groups which can still be generated by some finite subset of their elements. And I'll give you an example like this in just a minute. Okay, now let's take a look at some examples. Example number 0, which holds for any group G. If we take the set S to be the empty set, then since the trivial group contains the empty set, and since any other subgroup of G contains the trivial group, we have that the group generated by the empty set is just the trivial group consisting simply of the identity element. Now for example number 1, let's consider again the case where G is the group of integers and H is the subgroup nz for some integer n. Since this subgroup is just the set of all multiples of the integer n, by definition that means that H is generated by the single element n. So in this case, H is an example of a finitely generated group. Now just to emphasize the remark that I made a minute ago, notice here that the group G is an infinite group, but it's generated by the single integer 1. So here's an example of an infinite group which is finitely generated. For our second example, let's consider our cyclic group of order 6, together with the two subgroups H1 and H2 that we identified before. Now, it's clear from the definition that the cyclic group of order 6 is generated by the element x, since any subgroup which contains x will have to contain all of the powers of x, and so it will have to contain all of C6. It's also not difficult to see that the subgroup H1 is generated by the element x cubed, and that the subgroup H2 is generated by the element x squared, because in the first case, any subgroup of G which contains the element x cubed will also have to contain x cubed squared, so it will have to contain H1. And in the second case, any subgroup of G which contains the element x squared will have to contain x squared squared and x squared cubed, so it will have to contain H2. It's also true in the second example that the group H2 is generated by the element x to the fourth, because working in the cyclic group of order 6, x to the fourth squared is x to the 8th, which is x squared, and x to the fourth cubed is x to the 12th, which is the identity element. So any subgroup of G which contains x to the fourth will also have to contain H2, and that shows that H2 is the cyclic subgroup generated by the element x to the fourth. Now, moving on to our third example, the Klein 4 group with the three subgroups that we identified before, it's pretty easy to see that the Klein 4 group is the subgroup generated by the elements A and B. And it's also not difficult to see that H1 is the subgroup generated by A, H2 is the subgroup generated by B, and H3 is the subgroup generated by AB. Finally, in our example with the dihedral group of order 2n, the group D2n itself is generated by the elements R and S, since every element of the group is a product of powers of S times powers of R. The subgroup consisting of the rotations in the dihedral group of order 2n is generated by the rotation R, and the subgroup consisting of the reflections is generated by the reflection S. Now, one thing which you may have noticed about all of the examples that we've seen so far is that all of these groups and subgroups have been examples of finitely generated groups. And so now let's ask ourselves, what does a non-finitely generated group look like? And can we give a simple example? Well, one of the simplest examples of a naturally occurring group, which is not finitely generated, is the group of rational numbers under addition. To prove that it's not finitely generated, let's start with any finite collection of rational numbers S, and let's try to argue why the group generated by S can't be all of Q. Let's write the set S as the collection of rational numbers gamma 1 to gamma n, where each gamma I is pi over qi, with pi in the integers and qi in the natural numbers. Now, the original definition of the subgroup generated by a set, which is the intersection of all subgroups of G which contain S, is not always so easy to work with in practice. And so what I'd like to show in this case is that this subgroup generated by S is the same as the set of all integer linear combinations of the rational numbers gamma 1 to gamma n. In other words, I'd like to show that the subgroup generated by S is the collection of all rational numbers of the form a1 gamma 1 plus ... plus an gamma n, where the a1 to an's are integers. So let's call this set the set H. And let's try to argue first that H is the subgroup of Q generated by the set S. Well, first of all, we need to mention that H is a subgroup of Q, and that's pretty easy to verify, for example, by using the subgroup criterion. Now, the second thing that we want to mention is that because the set H contains each one of the elements gamma 1 to gamma n, it contains all of S, and therefore, by one of the facts that we mentioned after the definition of the subgroup generated by S, the subgroup generated by S must be a subset of H. Now, the final fact is that because any subgroup of Q must be closed under addition and taking negatives, it follows from the subgroup criterion applied to the subgroup generated by S that every element of H is also an element of the subgroup generated by S. In other words, this gives us the reverse inclusion that H is a subset of S. And now, because we have both of these inclusions, we can conclude that the subgroup generated by S is in fact equal to H. So that's the first step of our proof that Q is not finitely generated. Now that we know that for any finite subset S of Q, the subgroup generated by S is the same as the set of all integer linear combinations of the elements of S, let's let Q be the least common multiple of the denominators of the elements of S, and let's think about what happens when we take a generic element of H and multiply it by Q. Well, any element X of H looks like a sum of AI times pi over qi's for some integers a1 to an. And when I multiply that element X by Q, I can bring the Q on the inside of this finite sum. And then, noticing that Q is a multiple of all of the Qi's, the quantities in the parentheses here are all integers, so I find that Q times X is always an integer. But now I know that there are definitely rational numbers out there with the property that Q times those rational numbers is not an integer, so I want to use that fact to try to conclude that H can't be all of Q. That's pretty easy to do if I just consider, for example, the rational number 1 over 2Q. When I multiply this rational number by Q, I get a half, which is not an integer. So I conclude right away that the rational number 1 over 2Q is not an element of the subgroup generated by S. Therefore, that subgroup is not equal to all of Q. That proves that Q can't be generated by any finite set S. And so, in other words, Q is not finitely generated. Now, it's worth extracting one of the ingredients in the example that we just saw and making it a theorem in its own right. And that is that if G is a group and S is any subset of G, finite or not, then the subgroup generated by S is the collection of all finite products of elements of S and their inverses. In other words, it's the collection of all products of the form G1 to the U1, G2 to the U2, ... Gn to the Un, where the Ui's here are all plus or minus 1s, and the Gi's are all elements of S. The n here is allowed to be any natural number, so you can make this product as long as you like. Now, a couple things to point out about the set on the right-hand side. Number one, I'm not assuming that the elements Gi here are distinct, and so you're allowed to use elements of S over and over again if you want to. And number two, in this product, order matters in general because we're not assuming that the group G in the statement of this theorem is an abelian group. I'll give a version of this theorem for abelian groups in just a minute. Well, the proof of this theorem is much like the example that we saw. Let's let H be the set in the statement of the theorem. And let's notice three things about the set H. Number one, it's closed under products and taking inverses. That's pretty easy to check, and so it guarantees that H is a subgroup of G. Number two, H contains all of the elements of S, and so that guarantees that the subgroup generated by S is a subset of H. And number three, because the subgroup generated by S is itself a subgroup which is closed under taking products and inverses, the subgroup generated by S must also contain all of the elements of H. Now, just as before, these last two inclusions guarantee that H is in fact the subgroup generated by S, and that's exactly what we were trying to prove. Now, this characterization of the subgroup generated by a set is sometimes a little easier to work with than the characterization given in the definition as the intersection of all subgroups of G which contain S. As I mentioned just a minute ago, if G happens to be an abelian group, then there's another equivalent way to write the statement of the theorem that we just saw. In this case, the subgroup generated by S can also be written as the collection of all finite products of powers of distinct elements of the set S. So in other words, you just consider the collection of all G1 to Gn's, and here you can assume that the Gi's are distinct, and you think about all of the different ways of raising those to integer powers, which includes inverses and their powers, and then multiplying them together. That gives you precisely the subgroup generated by the set S. In the even more special case when S is a finite set and G is an abelian group, we can just write this as the set of all products of the form G1 to the A1 ... Gn to the An, where the AIs here run through all possible choices of integers. Now I want to talk a little more about cyclic subgroups, which remember are subgroups generated by a single element of a group. First of all, let's start with this definition. If G is an element of a group G, then the order of the element G is defined to be the smallest natural number k with the property that G to the k is the identity element, or infinity if no such natural number exists. Two common notations for the order of an element G are to write either absolute value of G or little o of G. Now, in what follows, I'm going to mostly stick with the first notation here. Now first, let's take a look at a few simple examples, just to make sure that we understand the definition. So in the cyclic group of order 6, what is the order of the identity element? Well, it's pretty easy to see that the order of the identity element in any group is 1. So 1 is the smallest exponent with the property that that element raised to the exponent is the identity. How about the order of the element x? Well, remember, I'm looking for the smallest natural number k with the property that x to the k is the identity. And since x to the 1, x squared, x cubed, x to the 4th, and x to the 5th are all distinct non-identity elements of this group, but x to the 6th is equal to the identity, the order of the element x is 6. How about the order of the element x squared? Well, x squared to the first power is just x squared. X squared squared is x to the 4th. But x squared cubed is x to the 6th, which in the cyclic group of order 6 is the identity element. Therefore, the order of the element x squared in this group is 3. Now similarly, it's not difficult to see that the order of the element x cubed is 2, since x cubed to the first is x cubed, but x cubed squared is the identity. And continuing in this way, we work out that the order of x to the 4th is 3, and the order of x to the 5th is 6. Now one shortcut in this last example is just to notice that x to the 5th is x inverse. So when you take x to the 5th to an integer power from 1 to 6, you just get x to the minus I. And as I goes from 1 to 6, x to the minus I traces out the elements x to the 5th, x to the 4th, x cubed, x squared, x, and then the identity element. Therefore, the order of this element in this group is 6. For another simple example, let's consider the dihedral group of order 6 generated by a rotation r and a reflection s. In this case, it's easy to work out the orders of the identity r squared, and the element s. And so we're left with just wanting to know what are the orders of the elements sr and sr squared. Well, sr to the 1 is sr, so the order of sr is clearly greater than 1. And using the relations in the definition of the dihedral group sr squared, which is sr times sr, or s times rs times r, is the same as s times sr inverse times r, which is s squared times r inverse r, which is the identity element. Therefore, the order of the element sr is 2. Now, in almost the same way, we find that sr squared also has order 2, because sr squared to the first power is clearly not the identity element, but sr squared squared turns out to be s times r squared s times r squared, and r squared s turns out to be the same as s times r to the minus 2. Now, in case you haven't seen this before, that follows from the relation that rs equals sr inverse. Because if we take r squared s and write it as r times rs, we can replace the rs in the parentheses here with sr inverse, then move the parentheses over and replace the rs on the left by sr inverse again to turn it into s times r to the minus 2. Now, as you can imagine, the same thing holds if you have r to the ns in a dihedral group. R to the ns turns out to be the same as s times r to the minus n. So using this fact here, just as before, we find that sr squared squared is the identity element, which allows us to conclude that the order of this element is 2. Now let's consider the group of integers, and let's ask what is the order of an integer n in this group? Well, here there are two possibilities, depending on whether or not this integer n is the integer 0. If n is equal to 0, which is the identity element in this group, then the order of n is 1. But if n is not equal to 0, then no matter how many times you add n to itself, you're never going to get back the identity element. So if n is not equal to 0, then the order of n is infinity. Now, here again, you need to remember that the group operation in this group is addition. So when we're using the definition of order, instead of considering powers of n, we're really considering multiples of n. But anyway, this is the answer in this case. The order of the identity element in this group is 1, but the order of every non-identity element is infinity. Now I want to prove a basic but important theorem, which also explains the reason why we called absolute value g the order of the element g. What the theorem says is that for any element g in G, the order of the element g is the same as the order of the cyclic subgroup generated by g. Now, just to make sure that you understand the subtleties of the statement, first of all, remember that the cyclic subgroup generated by g is the subgroup consisting of all integer powers of g, and that the order of a group is defined to be the cardinality of the group. So what this statement is really saying is that when you take the cardinality of the smallest group containing the element g, the cardinality of that group turns out to be the same as the smallest positive integer with the property that g to that integer is the identity. Now that statement is taken with the caveat that if one side of this equation is infinite, then they both are. Now I'd like to prove an even more precise version of this theorem, and I'll separate out the case of infinite order from the case of finite order. So first of all, if little g turns out to be an element of infinite order, then what I want to prove is that g to the I is never equal to g to the j when I and j are distinct integers. That guarantees that all of the elements of the group generated by g are distinct, so the cardinality of the group on the right-hand side is infinite. Now secondly, in the case when g has finite order k, then I'd like to prove that the cyclic subgroup generated by g is precisely the set of distinct elements identity g squared up to g to the k minus 1. And to make this even more precise, I'm going to add here the statement that in this second case, g to the I is equal to g to the j for integers I and j, if and only if I and j are equal modulo k. The first statement here is a conditional statement, so it's logically equivalent to its contrapositive, and that's what we want to try to prove. So let's suppose that the negation of the conclusion holds, and what we want to prove is that the negation of the hypothesis holds. In other words, let's suppose that there are integers I and j, with I not equal to j, with the property that g to the I is equal to g to the j. Under that hypothesis, we'd like to prove that the order of the element g is actually finite. Well, without loss of generality, by interchanging the roles of I and j if necessary, we can assume that I is less than j. And then multiplying both sides of this equation by g to the minus I gives that g to the j minus I is the identity element. And since I is less than j, the exponent j minus I is guaranteed to be a positive integer. Well now, the fact that there is a positive integer with the property that g to that integer is the identity means that the order of the element g is less than or equal to that exponent, which guarantees that the order of g is finite. That establishes the contrapositive of the conditional statement in 1, and so it proves that it's true. Next, let's see how to prove the second statement. So let's suppose that the order of g is a natural number k, and that g to the I is equal to g to the j for some integers I and j. Then, multiplying both sides of this equation by g to the minus I gives that g to the j minus I is the identity element. And now what I'd like to do is to appeal to the division algorithm, which guarantees that there are integers q and r with the properties that this exponent j minus I is q times k plus r, and that r is bigger than or equal to 0 and less than k. Then, since the identity element is g to the j minus I, by using properties of exponents, I can write this as g to the k to the q power times g to the r. And since the order of the element g is k, I know that the quantity in the parentheses here is the identity. Therefore, I find that the identity is equal to g to the r. But now I'd like to use the fact that the order of an element is the smallest natural number with the property that when you raise that element to the power, you get the identity element. So in this case, since k is the smallest element of the natural numbers with the property that g to the k is the identity, and since the remainder r is required to be bigger than or equal to 0 but strictly less than k, I can conclude that r must actually be equal to 0, and therefore that j minus I is actually equal to q times k. Well, that's the same as saying that I is equal to j modulo k. That gives me one direction of this biconditional statement. Now for the other direction of the biconditional statement, if I is equal to j modulo k, then it means that j minus I is q times k for some integer k. And then by a similar argument, I get that g to the j minus I is the identity, which guarantees that g to the I is equal to g to the j. So the other direction of this biconditional statement is not a lot different than this direction, and in fact it's a little bit easier. In any case, I can conclude from this that the cyclic subgroup generated by the element g consists of the distinct elements g to the 0, g to the 1, out to g to the k minus 1, and therefore the order of the cyclic subgroup is the same as the order of the element g. That completes the proof of this theorem. Now the final thing that I'd like to talk about in this video are lattices of subgroups of groups. And this is pretty intuitive, so instead of giving a super rigorous definition, let me just say that a lattice of subgroups of a group is a diagram which illustrates the subgroups of the group. And let me show you a few examples. First of all, earlier in the video, we saw that the subgroups generated by A, B, and AB are all proper subgroups of the Klein 4 group, and together with the group itself and the trivial subgroup consisting just of the identity element, this is a complete collection of subgroups of the group G. So to draw the lattice of subgroups of the Klein 4 group, we start by writing the group G at the top, and then listing out the subgroups below it, with line segments indicating set containments, and with the relative positioning of the groups in this diagram corresponding to the orders of the groups. Since the orders of the groups H1, H2, and H3 are all 2, they're all listed on the same level here. For the cyclic subgroup of order 6, we listed 2 proper subgroups of the group, which were groups of orders 2 and 3 respectively, and it's not difficult to show in this case that these groups, together with G and the trivial subgroup, account for all possible subgroups of the group. Therefore, the lattice of subgroups looks like this, with the identity at the bottom, followed by H1 and then H2 positioned slightly higher, to indicate that it has a slightly greater order than H1, and finally with G here at the top. And our final example, the dihedral group of order 6. Well, here before we mentioned 2 subgroups which were the subgroup generated by R, a subgroup of order 3, and the subgroup generated by S, a subgroup of order 2. However, in our calculations with orders of elements, we also found that the elements SR and SR squared were elements of order 2. Therefore, by our theorem, they generate subgroups of order 2. And now, it's not difficult to show that this collection of groups, together with the trivial group, accounts for all subgroups of the dihedral group of order 6. Therefore, the lattice of subgroups for this group looks like this, with G at the top, the subgroup of order 3 listed next, and the subgroups of order 2 listed next, and then with the trivial subgroup listed at the bottom. Okay, well that's the end of this video. I hope you enjoyed it. In the next video, we're going to talk about a super useful theorem which has already been mentioned several times, which is Lagrange's theorem.